Hello, my name is Craig Teague. I'm a professor of chemistry and I'm also the director of Ingenuity, our core curriculum, and the first year seminar is part of Ingenuity. Today I'd like to do a brief presentation about why elements have different colors. So the nature of light in the 1800s, it was firmly established that light behave like a wave, and we can describe waves with frequency and wavelength, and they have different properties depending on the values of those things. But the point is that no matter what, light behaves like a wave. And you've probably had the experience of, or seen a picture of, you pass white light through a prism or perhaps a diffraction grating, and you get a rainbow, and you get this full spectrum, and there's no gaps or there's no breaks. And you may have learned that the colors are always in the same order: red, orange, yellow, and it spells out Roy G. Biv going in this direction. So the light is a form of energy, and white light, you get this continuous rainbow. So I want to start by thinking about street lights. Have you ever noticed the street lights are either yellowish or bluish white and never any other colors? So why would that be? And it turns out that it's because of what's inside the street lights. Street lights are always made from either sodium, which glows yellowish, or mercury, which glows bluish white. And it's always using one of those two things, which is why street lights are always one of those two colors. So at this point, I'm going to switch screens and do a brief demonstration. So give me just a minute to switch screens. Okay, so here you can see a discharge tube that has hydrogen in it. And what we're doing in this tube is that it's a thin glass tube and it has only hydrogen, and we're passing an electrical current through that gas inside the tube. And that's all we're doing, passing an electrical current. This is similar to what happens with lightning in the atmosphere, except that there's very little hydrogen in our atmosphere, and this tube is composed completely of hydrogen. So next, I'm going to show a different tube, and this tube is helium. And you can immediately see that it's a different color. It's not even close to the same color. This is helium. This is argon. Argon's present in about 1% in the Earth's atmosphere. This is carbon dioxide. And so you may know that carbon dioxide is a molecule and not an atom. So molecules have distinct colors as well. This tube is broken. And this tube is nitrogen. And here finally is neon. Now neon always glows this color. So if you see a neon sign that is a different color, it's probably not neon. So I will show those once again, starting from the beginning. This is hydrogen. This is helium. This is argon. This is carbon dioxide. This is nitrogen. And this is neon. So I'm going to switch screens back now. Okay. And we're back to this screen. So that was our discharge tube demonstration. And you can also do this by using a flame instead of passing an electrical current through. And in fact, that's how the scientists working in the middle of the 1800s first did this sort of experiment to realize that elements had different colors. So let's talk a little bit more about that. So this would be our tube of hydrogen, the first tube that we saw. You can pass it through some kind of wavelength selector, whether that's a prism or some other thing. And you can see that when you do that, you do not get a full rainbow of colors. In fact, you get only these lines of color, very thin lines of color, separated in some cases by wide gaps. So you do not get the full complete spectrum, and so we call this a discrete spectrum. It's not continuous. It's a discrete line spectrum. And so if you just put, you're sort of taking this screen and putting it right here, there's a prominent red line, and then there's a line here and a line here, but there's nothing happening here. There's no light emitted in these big dark regions. Furthermore, our eye cannot sense all regions of light. And so this is what's called the visible series, but there's also another series of lines in the ultraviolet and yet another series of lines in the infrared. And you might notice that the spacing changes in somewhat of a regular way. In other words, the largest space in the visible is here, and then the spacing gets narrower. The largest space in the infrared is here, and then the spacing gets narrower. And that ultimately tells us something about the hydrogen atom. So our eye is a chemical detector, but it's not a complete chemical detector. And there's these other series in other regions of the spectrum. So it turns out that every element has a unique line spectrum. Every element is distinct from every other element when you take it and spread out its light. And so here's mercury, here's helium, here's lithium. Some elements have a lot of lines like barium, and other elements like hydrogen don't have that many lines. But every single element is different in terms of its spectrum. And scientists have started to realize this. If you can get a pure enough sample, then you can always distinguish what element is present in the sample by either passing an electrical current through it or putting it in a flame and separating the light that comes out. And so an interesting story as related to that is that people also did that with sunlight. And so you may know that the sun is mostly hydrogen, but it has a number of other elements present in it. And it turns out that when people separated out sunlight and they were able to identify the elements in the sun based on the lines that showed up in the spectrum. But there was a problem. There was a set of prominent lines that no one had ever seen before. And scientists realized that there must be an element in the sun that they had never observed on Earth, because they could not find any other lines on Earth-based experiments that could find those that matched any known element. And so they named that element helium, or helios, or of the sun. So they realized that there was an element that they had never seen before that the sun must have, and that's why helium has the name that it does. It was later discovered on Earth, and that is a story for another time. It's also an interesting story. All right, so let's return briefly to our street lights. Here is sodium at the bottom. Notice that sodium has very prominent yellow line. It's actually two very closely spaced yellow lines, and that's why sodium street lights are yellow. Mercury's spectrum is more complicated, and it looks like it's got all these different colors, but our eye can't distinguish all these lines, and all these colors together to our eye looks like bluish white. So in Ravelli's chapter 2, there was a discussion about this, and Planck, who is shown here on the right, Max Planck, was working on a completely different problem and realized that by using a mathematical technique, he was able to show that he could get his theory to match an experiment if he assumed that there were fixed packets of energy, fixed or quantized energy, discrete packets, okay? Einstein, in one of his papers published in 1905, started talking about essentially particles of light, photons, which we now call them. And so those were individual discrete little pieces of light. And so this is a very different picture of light from what was present before Planck and Einstein started working. It turns out that the other person in this picture is Niels Bohr. Niels Bohr had the next advance in terms of trying to understand why the elements were different colors. This was not something that Planck and Einstein worked on, but Bohr realized that he could take their ideas and extend them a little bit, and perhaps we could get somewhere. So Bohr's model of the atom is sometimes called the planetary model of the atom. So it looks something like this. There are electrons, which are negatively charged, and they're orbiting the nucleus, which is positively charged. Bohr did not discover either one of those things, but Bohr's key contribution was, where are the electrons as they're orbiting the nucleus? And here's the really interesting thing. People knew that electrons were outside the nucleus, but the thing Bohr said, or what he theorized, what he hypothesized was the electron could be here, or it could be here, or it could be here, but it cannot be off orbit. There is no way for the electron to be, say, here or here. It is not possible for the electron to be off the orbit. That is surprising. Why would that be the case? But that may be that could have an impact on the experimental results that we've been talking about. I'll just make a brief note here. It's often the case that this is the picture of an atom, or perhaps this picture of an atom is that people have in their minds when they think about an atom. This is really the Bohr model, and we have advanced our model of the atom, and it really doesn't quite look like this. And to understand that, you need more quantum mechanics. However, Bohr's model was successful at explaining the spectra of things. And so here's the same picture we saw on the previous slide. If you understand or realize that these electrons orbiting the nucleus have an energy associated with them, and the energy depends on how far away they are from the nucleus. So the closest one to the nucleus has the most negative energy, and that's this n equals 1 level right here, corresponds to here. So these are different energy levels that correspond to the different orbits. Each orbit has a different energy. And what Bohr realized was that if these orbits were fixed, then these transitions between, in other words, if an electron was here on this orbit and jumped down to this orbit, it would always emit the same amount of energy. It would never emit some energy corresponding to if the electron was here. So it turns out that when you do that, when you have these fixed orbits and these fixed energy levels in the atoms, the transitions between, they cannot be a continuous spectrum because these energy levels are not continuous. They are discrete energy levels, which gives rise to discrete lines in the spectrum. And these lines are colored to show you this will be a hydrogen spectrum, and these are the colors of the photons that come out of the atom when the electron transitions from a higher state to a lower state. Notice that the energy levels are not equally spaced, and that has to do with why that confirms why the lines in the spectrum are not equally spaced as well. So if we extend that just a little bit further, and this Bohr's model also shows this is the visible spectrum. And if we saw earlier, there was a series down in the ultraviolet and a series in the infrared. Bohr's model explains all these different series. And so finally, we have an understanding of why there were these different colors of light. Bohr's published this in 1913. So this had been a mystery for over 60 years as to why the elements had different colors of light. And finally, we are understanding it, but only because energy is quantized. Light can be quantized. We also have conclusive evidence from other experiments that light is a wave. We can't just throw out those other experiments. And so now we have this more complicated picture of what light is. And it's basically what we say is its wave-particle duality. Sometimes it has the properties of waves, sometimes it has the properties of particles, and a particle of light is a photon. So a brief note about where these images came from, except where noted, they all came from a general chemistry textbook. And thank you for watching.